All right, everybody, 10 o'clock. Welcome in to ME3005, also known as your favorite class, obviously. Okay. Today's agenda, we're going to continue the fatigue. We're going to finish up this lecture number 10, notes on fatigue. We got a long practice problem today ahead of us that kind of incorporates everything that we've done so far. So I particularly like the practice problem here that we're going to do today. Couple of announcements. Again, I've posted a homework 8, which is on fatigue, which will be ungraded. So it's posted, full solution available. I'd make sure to take a look at that before the final, because you're going to have a question on fatigue for your final. All right. Your final exam for this class is a week from today, almost about exactly a week from today. 1 week and 1 hour from today. It's going to be on Teams. We're kind of in the midst of exam 2 right now as well. People took it yesterday in the lab slot, and people will take it tomorrow also if you have the Thursday lab. I have graded all of the exams from yesterday already, though I haven't posted any grades because I'm waiting until everybody sort of finishes on Thursday before I post any grades. I will say, Tuesday, good job. I was impressed. All right. It's a little bit difficult for me to put my finger on and get a pulse of what's going on with the class in this sort of weird situation that we have right now. But after grading those exams yesterday, man, I was impressed. All right. So damn, good job, guys. Like, I know this is not an ideal situation, but you guys took that thing to Pound Town. So keep that thing going. And Thursday, you got a lot of work cut out for you to keep up with Tuesday. Okay. So rawr, good job. All right, keep it going. I'll release the grades for everybody after I've graded all the tests on Thursday, and I'll also post the solutions for both exams on Thursday night. Okay, so you'll have your grade whether you took it Tuesday or Thursday by the end of the day on Thursday. Okay, so there you go. Any questions? All right. Well, how do we like the meme today? You guys even seen this? Like, most of you were born after this movie came out, but Keanu Reeves, he looks the same anyway. So he just never ages. Sandra Bullock, still looks, relatively young considering her age now too as well. So over 25 years ago this movie came out. Dang. All right. Anyway, they shouldn't call it speed because it, has direction. It should be called velocity. All right. Funny math joke. Okay, so let's get back to it with our fatigue stuff and whatnot. So here we are back on the writing pad. And let's I'll just pull up the notes here and talk about things we've kind of gone over so far. So remember, we were kind of making modifications to the endurance limit using a variety of different correction factors. So we looked at, specifically in this class, surface correction, size correction, and load correction. And so we're modifying the pristine value. Where's my pointer? Modifying the pristine value here, SE prime, by all these factors. In this class, we're specifically focusing on surface, size, and load. There are other modification factors that exist, though we don't necessarily talk about them in this class. Someone mentioned temperature. I think that was Jordan that mentioned temperature before. There are temperature modifications as well, but we don't really deal with that in this class just for time reasons. Okay, so we talked about surface modification here. It's A SUT to the B, where A and B are these coefficients that are gotten from experiment based on a variety of different surface types that we have. Did an example problem. Then we talked about size correction. And again, size correction is a little bit strange in that you're basically accounting for a variation in surface area to volume ratio. The more surface area that you have on your piece, the higher probability of, your piece failing prematurely from this, sort of cyclic stress that we're applying. And so this chart is trying to correct for the fact that you might have different size of pieces. And not just different size, but different shapes. And not just different shapes, but different loading types. So we also talked about the difference between rotating and non-rotating bending. Again, with rotating being sort of like this on a motor where all points on the outside of the body are experiencing the same maximum compression and tension, versus sort of this non-rotating bending, which was kind of like this sort of situation, where only like the top and bottom pieces are experiencing the maximum compression and tension. So we did an example problem here showing rotating versus non-rotating behavior. And finally, we concluded last time with our correction factors looking at load corrections. And so talking about how we modify endurance limits for the loading types that we might have. Again, bending, something like this, axial loading, kind of this like tension compression over and over, and then torsion, sort of something that looks like, like this. All right. So you're revving the engine on the motorcycle over and over. Okay. Some sort of like torsional effect. All right. We also talked about stress concentration factors. static and fatigue concentration factors. And so you go to the back of any good mechanics textbook, you're going to see a bunch of charts that lay out static stress concentration factors. So we talked about what those are, and we had sort of the classic example here with like a hole in a plate. And the idea here is that stress is amplified around some of these stress concentrators. So like holes or fillets or radii or whatever inside of your piece. Stress is amplified in a static condition, and it goes with charts that look something like this. So if you have a certain, hole diameter versus the width of the plate, you can determine what your static stress concentration factor is given that particular ratio of the hole diameter to the width of the plate. All right, it's pretty straightforward. So this is pretty easy to get for static conditions, but we have an additional piece of information that we need to calculate what our fatigue stress concentration factor is, and it's different than the static factor. So don't go and be using the static factor on the test. All right, you got to use the fatigue concentration factor, which is slightly different. The fatigue concentration factor here is again the similar idea, is that what is the maximum stress around this, stress concentrator, a fillet, a notch, a hole, etc., divided by, here this should be like the stress amplitude that we apply or the shear amplitude that we apply. And we need an additional correction factor, which we call notch sensitivity. And so we talked about notch sensitivity last time, and it's an additional sort of constant based on sort of how tough the material is that will either further amplify or kind of keep the static stress concentration factor the same as we move from a static stress concentration to a fatigue stress concentration factor. And so we have different notch sensitivities here, this variable Q, both in sort of a traditional normal stress loading, and we also have a factor if we have like a shear loading. So here we have KF for normal loading and KFS for shear loading. And we have charts that basically tell us what this notch sensitivity factor is, given some certain ultimate tensile strength and material that you have. So these various lines here for different ultimate tensile strengths of steel, and then this dashed line here is for aluminum. So again, what's your notch radius? Come to this chart. What's your ultimate tensile strength? You can pick off your notch sensitivity value, couple that with the static stress concentration factor from charts that exist like in the back of your book. That will give you your fatigue concentration factor, telling you how your stress is amplified against some particular notch inside of your fatiguing piece. All right, a little bit complicated, a little bit long, but again, it's just something we got to do because of this like empirical nature of fatigue. It's a little bit annoying, but it is what it is. All right. Famous phrase, it is what it is. All right. So let's continue now with the lecture, and we're going to move on, and we're going to talk now about some of the, oh man, I have issues with my writing pad. Come on, turn it off, turn it back on. Sometimes when I connect the writing pad, the pen doesn't sync up with where I'm actually touching on the pad. Okay, so turn it off, turn it back on, and it works just like everything in engineering. All right, so what we've talked about so far, quickly. Your endurance curve is something that looks like this. So here, number of cycles to failure, stress amplitude. Here is your ultimate tensile strength, SUT. And we saw that we generally have lines that look something like this. Okay, this is a sort of a gross exaggeration, but you get the idea. And here, this is your endurance limit, SE, right? And we know that we can modify this endurance limit and basically modify these curves for size, surface, temp, load, etc. Okay, and all the modifications that we've done so far tell us how to modify this curve based on these phenomena. And so some modified curves that we might see might look something like this. Oh boy, it's like that. I want it to plateau. So here might be some modified curve. You might get a modified curve that's slightly higher than what you get from the RR Moore high-speed test. Okay, so this here is like pristine test, and these are like modified. Okay, so if we run a pristine test, we get the pristine endurance limit, which is like this value here, which we know is like SE prime. Okay, this is the pristine endurance limit. And the modifications that we've made are modifications to this based on size, surface, etc., that are giving us these values here. This is like a modified endurance limit SE for size, temperature, etc. We might also have a different modified endurance limit here which is modified by size, surface, temperature. Maybe we have a much smaller size, so a lower surface area to volume ratio. Okay, fine. We have a different modified endurance limit. So everything that we've done so far has been just like looking at how the endurance limit changes. How we get a modified endurance limit from a pristine endurance limit. But we're neglecting a huge portion of this endurance curve, okay? We're neglecting basically everything that's going on up until the endurance limit. So we're neglecting like all of that information so far, right? Yes, it's nice that we can like calculate a modified endurance limit, but what about everything that's happening like before we get to the endurance limit? It would be nice if we could come up with some expression that allowed us to calculate, all right, if I have some applied load, let's say some stress amplitude here, how many cycles am I going to get to failure? Okay. Which would be like these x-axis values. It would be nice if we could come up with an expression based on modifications to the endurance curve that would allow us to predict number of cycles to failure given some applied stress amplitude that was greater than the endurance limit. Okay, hopefully this makes sense. So let's put this in words. Would be nice to be able to predict number of cycles to failure if my stress amplitude that I'm applying is larger than my endurance limit, okay? A modified endurance limit. So take into account the size, take into account the surface, take into account the loading type, etc., and then modify what that endurance curve looks like and give us some prediction for what is this number of cycles to failure given some stress amplitude. Would be nice, okay? There are a lot of models that do this. We're only going to talk about the model that is specifically used for steel with high cycle failure, right? So there are many models that do this. We're specifically going to focus on just one because, you know, complicated. Um, just a second. My notes not include? Oh, my notes aren't including this information. Huh, I think I might have given you guys a bad set of notes. Do you guys have like slides 15 and 16 on your electronic copies of your notes or not? Oh, yeah, okay, you do have it. All right. For some reason, I just like don't have it here in front of me. But that's okay. I can make it happen. All right. So let's talk about this. Estimating cycles to failure. I don't need no notes. All right. There are many models that exist. The only one we're going to focus on here is a model for completely reversed stress. Has the following. Completely reversed stress state. What this basically means is that my mean stress is 0. Okay, remember when we talk about our cyclical fatigue that we apply? When we have completely reversed stress, that means we have an equal amount of compression and tension being applied on our piece. All right, so the mean stress is 0. And we have steel, which is in sort of high cycle fatigue. So what do I mean by that? Is that we have numbers of cycles to failure that are somewhere between, let's say, 1,000 and 10 million. So here, 10 to the 7th, and on the low end, 10 to the 3rd. Okay, so that's approximately the values that we want. All right, so approximately these values. And last thing I'll say here is that we have to have a load that's applied between the endurance limit and the ultimate tensile strength, obviously. So that gets us in the region that would give us some predictable cycles to failure. If you have a stress amplitude that's below the endurance limit, then obviously you're never going to fail, okay? And if you have a stress amplitude that's above the ultimate tensile strength, well, you're just going to fail after one cycle, right? So yeah, that's the general range that we're interested in here. Okay, so here's the model. And again, this is empirical, but here's the model. Number of cycles to failure equal to the stress amplitude divided by a constant A. This is not the same constant A from service modification. This is a different constant to the one on B. All right, so here's your model with all those sort of assumptions laid out. Okay, we have some constants we need to worry about. Okay, this constant A here is what we call the fatigue strength fraction, little f squared, times the ultimate tensile strength, FUT squared, all on the endurance limit that's modified, SE. It's modified endurance limit, SE. B, this is negative 1/3 log base 10. So this is not a natural log base 10. Fatigue strength fraction F, SUT, ultimate tensile strength, over modified endurance limit. Okay. I'm not going to define these. I think all these things are kind of well defined, except maybe we define little f. This is fatigue strength fraction. Okay. The fatigue strength fraction, this just comes from, again, experiment. Everything just comes from experiment. Just do experiments. If you don't know what you're doing, just do an experiment. And that seems to be the method here. All right. So let me get my fatigue strength fraction chart. Here looks something like this. Okay. This kind of comes from your Shigley book. Right. So the fatigue strength fraction F, this little sort of script F here, it's based on the ultimate tensile strength of the steel that you have. So the lower the ultimate tensile strength, the higher the fatigue strength fraction. So there you go. And here it's going to range usually from like 0.75 to 0.9, sort of depending on the ultimate tensile strength of your steel. Okay, so a lot of just like empirical stuff that you sort of have to keep track of. So there you go. That's your model for calculating cycles to failure. Here, given some stress amplitude that's applied between your ultimate tensile strength and your endurance limit. So specifically for steel, specifically for high cycle fatigue. Okay. All right. Let's put it all together. Yeah. Let's get together. Yeah. And let's do an example. Complicated example, but it is one that sort of brings together every single thing about fatigue that we've talked about so far. This comes from page 17 of your notes. Here we have this shaft supported by ball bearings at A and D. Okay, so A and D is kind of like the left hand and right hand side over here. Right. We have resulting reaction forces R1 and R2, which you can sort of see here, R1 and R2, from this applied 6.8 kilonewtons. We have a 6.8 kilonewtons non-rotating force All right, so these things are steady in this 3-point bend configuration as the shaft is rotating around. All right. Given that each shoulder has a static stress concentration factor of 1.65, so each one of these shoulders here, like at points B and C, has a static stress concentration factor of 1.65. So we'll need to modify that using the shear correction factor. And the material is made of a machined steel with an ultimate tensile strength of 690 MPa. Determine all of these things. We want to find the modified endurance limit at point B. This is kind of our point of interest here for this piece. Estimate the maximum reversing bending stress and assume the fillet radius between the changing diameters is 3 millimeters. Okay, so this going from a diameter of 32 millimeter shaft to a diameter of 38 millimeters. We're going to assume the fillet radius here at point B is 3 millimeters. We want to determine if the material will yield with this yield stress of 590 MPa. So meaning, am I exceeding 590 MPa on my piece? And if not, estimate the cycles to failure. Dang, I got everything in this problem. Okay, maybe another 30 seconds and then we'll get after it. I'll bring in the figure too, to the example. I know it's a lot to try to make the figure. We've just been building up to this particular problem for like the last week, more or less. Talking about modifications to the endurance limit, talking about concentration factors, talking about cycles to failure. Goddamn, complicated. Okay, let's get after it. Want to keep your ink annotations? No. Okay, so here we are. This is sort of the shaft that we have in question here. A couple pieces of information that I'll sort of note here. We have static stress concentration factors at each one of the shoulders, which is 1.65. It's important to know. We have ultimate tensile strength, 690 MPa. This is made out of steel. And we have a yield stress, which will come into this later, 590 MPa. Right. First thing we're asked to find, part A, the modified endurance limit at point B, which is here on the structure. All right. This is kind of our point of interest here. We can see we have like this shoulder going on here, so this is going to be important to us. It's where we're going to have sort of stress concentrations and going to be like our highest likelihood of failure. All right, so let's do it. Generally, if we want to calculate the modified endurance limit, we'll just go on our business of using our correction factors. So the modified endurance limit, let's just include all of the ones that we've talked about so far. So load modification, size modification, and surface modification, all modifying the pristine value. Right, this is our general strategy. First thing we're going to want to do is we're going to want to calculate our pristine value. So for this, we get to the chart that tells us what the pristine value is given the material and yield stress that we have, or sorry, ultimate stress. So this is the chart that you want to go to. Here we have a steel with an ultimate tensile strength of 690 MPa. So we're kind of in this range here, an ultimate tensile strength less than 1460. So we're going to use this general formulation to calculate the pristine endurance limit. So 0.504 times the ultimate tensile strength is what we're after here. My ultimate tensile strength, 690 MPa. So I'll have a pristine endurance limit here, 340 MPa. 348. Kind of an important intermediate value that'll feed into the right-hand side of the equation above there. Okay, load correction. This one's kind of easy. Again, we'll just kind of go to our equation sheet or go to the notes and see what is the load modification for bending. And obviously, since the RR more test is done in bending, our load modification is going to be 1 here. Since we have sort of a bending situation, we're in like 3-point bend with this current configuration. Our load modification equal to 1, and it's because we're in bending. Okay, so we don't really have to modify for our load condition, which is nice to know. All right. Next, maybe we'll do the surface. The surface is kind of the next easiest. Remember, our general formula for that is like ASUT to the B. We're told in this particular problem that we have a machined surface. So maybe we'll make a note here. So we'll go to our equation sheet, look at our chart. We're in metric units here. So for a machined piece, something with a machined finish, the value of A that we want in metric units here is going to be 4.51, and the exponent B, negative 0.265. So our exponent A, B. So that's for this like machine surface, okay? So 4.51, we're going to put the ultimate tensile strength here in metric units. Uh-oh. Lost my connection, my bad. Okay, there we go. Here's this 4.51 times our ultimate tensile strength, 690 MPa, to my coefficient of B, negative 0.265. And here I'll find that my surface modification for this problem, 0.798. So we're just making our way through with our modification values. So kind of intermediate results here. Last one we need is our load modification. Or sorry, our size modification. Right. So here we've got circular shaft. And it's up to us to decide whether we're in rotating or non-rotating bending. All right. Let's come back to this problem statement here and take a look. We're told we have a 6.8 kilonewton non-rotating force. All right, so this 6.8 kilonewtons here is stationary. All right, it is not rotating with the bar. So this is not rotating with the bar, but the shaft is spinning about some axis, right? So it's kind of like spinning around this like dashed axis here. So in this situation, every single point on the outside surface of this piece is going to be experiencing the maximum tension and compression. So while it says here that we have a non-rotating force, it's because this force is just held stationary. Because this thing is rotating, the piece is actually in a rotating bending mode. Okay. So this is circular shaft. Rotating mode. Okay. So in order to calculate this properly, we're going to have to go to our size modification chart, again, which is this guy here. So for a circular shaft with rotating bending, my A95 value is 0.0766 times the diameter of the piece squared. So let's go ahead and copy that in our problem. Okay. We also have this general formulation that the effective diameter is the square root of A95 on 0.0766. So with these two things kind of together, you can see that like the 0.0766 will cancel with the 0.0766. Hopefully we sort of like see that. And the diameter of my shaft, because I'm in this rotating mode, is just going to become the effective diameter of this piece. Okay. So the effective diameter here is whatever the diameter of the shaft is. Now the question is, what's the diameter of the shaft? Because we're at this interesting point on the piece where we're going from a diameter that is 32 millimeters to a diameter that is 38 millimeters. So I'll remind you kind of what the figure looks like here. At point B, which is our point of interest, we're going from 32 to 38 millimeters. So for conservative design, what value should I pick for my diameter? You want to pick the smaller one here. You want to be conservative with your estimates. So you'll pick the 32 millimeters as your dimensions here. So my effective diameter in this problem, 32 millimeters. All right. So we go back to our size correction chart and we look at where does that 32 millimeters fall in our calculation range. So here we've got a situation where my effective diameter is between this 2.79 and this 51 millimeters. So the equation that I'm going to use for my size correction is this equation here, 1.24d to the negative 0.107. So therefore, my size correction is 1.24 d to the negative 0.107. Okay. This is 1.24, my effective diameter here, 32 millimeters to negative 0.107. This is going to give me a size correction for this particular problem, just 0.856. All right. Finally, we're ready to calculate what is our modified endurance limit. Okay. So recall our equation that we're sort of using to govern this all the way back up here. We'll do load, size, and surface correction in that order. So my load correction, 1, we're in rotating bending. My size correction, which is coming in next year, is 0.856. And my surface correction, which I calculated before up here, 0.798. This is all modifying my pristine value, which I calculated before, 348 MPa. All right, so after all that rigmarole, my modified endurance limit here, 238 MPa. And this closes out part A of our problem. All right, very exciting. Moving on. Next part of the problem. I want to estimate the maximum reversing bending stress at point B. Assume the fillet radius between the changing diameters is 3 millimeters. All right. So the reversing bending stress, this is the stress amplitude. So B. What I'm asking is, what is my stress amplitude at point B? All right. Now, this is a kind of an intense process here, because the general idea here is that to get the stress amplitude, we need moment at B. And that's because generally my stress amplitude is going to be something like my over I, okay? Where m is the moment that is applied either positive or negative at this piece at that particular location, right? Furthermore, I need to modify what I would normally calculate as the amplitude by the fatigue concentration factor, so I also need that fatigue amplification factor as well, all right? And so the total stress amplitude is something like the fatigue concentration factor my over I. So I need all of these things specifically at point B. So that's where we're going. Now, all of you are going to cry because we have to figure out what the moment is at point B, which requires like a shear and bending moment diagram from like statics, okay? So let's hear it. Come on. Let's all grumble. Grumble, grumble. Yeah, okay. All right. So to find moment at B, I need free body diagram. Okay, so my shaft, I'm just going to draw it as one shaft here because the dimensions of the shaft are not particularly important for me at this time. The important bits are that I have 6.8 kilonewtons somewhere over here. I have a reaction force, R2, and I have a reaction force here, R1. You can go back to the figure and sort of remind yourself what the dimensions are to the 6.8 kilonewtons, but it's going to be something like 325. This is in millimeters. And on the right-hand side here, we have 225. Okay. If I give you something like this, using information that you have from statics, you should be able to figure out what R1 and R2 are. Okay. So using statics, that's like the sum of the forces equal to 0 or the sum of the moments equal to 0. Let's say you can do that about like either the left-hand side or the right-hand side. You'll get that the reaction force here, R1, is 2.78 kilonewtons. And the reaction force, R2, is going to be 4.02 kilonewtons. Together, that best add up to 6.8, or I done messed up. All right. I still have not found what is the moment at point B. All right. I'll remind you that point B is somewhere over here on this structure. Right. Specifically, it's 250 millimeters from the end. So there are a variety of ways that I could calculate what is the moment at B. The easiest is probably to just cut through that blue line there on your beam. Okay, so here we are, this is point B. We've got this R1 force that's pointing upward here, 2.78 kilonewtons. I've got a distance to point B, 250 millimeters. And when I make this internal cut, I'm balanced by a shear force at point B and also by an internal moment at point B. Okay, getting nightmares from statics yet? Yeah, you are. Okay, basically the idea here though is that the moment at B, once you sort of like do all this analysis correctly, you're going to get 2.78 kilonewtons. multiplied by this moment arm that exists, which is 0.25 meters. And so that you'll have the effective moment at point B from the kind of loading situation that we have right now, 695 Newton meters. This is going to feed into the stress that we calculate at point B. So this is just another intermediate sort of value here. All right. Continuing. Now, let's calculate unmodified stress amplitude. What do I mean by unmodified? We're not modifying it by any concentration factors at this point. So let's call it an unmodified value stress amplitude prime. Right? This is specifically at point B. This is going to be something like the moment at B times this variable y, which we'll talk about in a second, over the area moment inertia I. Right? Again, I want conservative sort of estimates for what the stress is at point B. So I'm going to say that I'm going to take this smaller section of the shaft. And so here, when I'm going to calculate the stress amplitude, which is unmodified by any like concentration factor at this point, it's just going to be the moment at point B, 695 Newton meters, multiplied by y. That's the distance from the center of the cross section to the point where the highest stress would occur. That's the outside, which is the radius of this piece. So if the diameter is 32 millimeters, then we have 0.016 meters. This is all over the area moment of inertia. Smaller area moment of inertia here. Pi on 4 times the radius squared, 0.016 meters. Sorry, not squared to the fourth. Or we'd get the sort of the stress amplitude, which is unmodified at this point at point B. We can calculate this as 216 MPa. Okay, again, another intermediate value. This is unmodified. But we're told that there's this like shoulder as we go from the 32 millimeter section to the 38 millimeter section. So, however, at shoulder, we're told that we have like a fillet radius, which is r is equal to 3 millimeters. And we're also told that we have static stress concentration factor KT of 1.65. All right. I still need sort of this modified stress amplitude to continue with my problem. So sort of this unmodified amplitude, which is the fatigue concentration factor, Kf, multiplied by my pristine sort of unmodified stress amplitude. So I need the fatigue concentration factor. The fatigue concentration factor is not the static stress concentration factor, all right? Remember that this fatigue concentration factor, if you go back to the notes, is something like 1 plus Q times the static value, KT minus 1. All right? I know this KT value, it's right up there, 1.65, but I need this value of Q. Remember, this is my notch sensitivity factor. All right? This value of Q is obtained from some of the charts that we've shown before. Here are these charts that are of interest to us. So the notch sensitivity charts. So in order to read this chart, I have a normal stress that's applied. I'm kind of looking at the chart on the left-hand side here. At the shoulder, the radius of my notch is 3 millimeters. So here I'm looking at this like 3 millimeter value. Now I also have to pick off the correct black line here. I know that the ultimate tensile strength of this particular piece is 690 MPa. So here this is 1.4 GPa, 1.0, 0.7 GPa. That's approximately 690 MPa. So I'm more or less looking at this black line here when I'm trying to pick off my notch sensitivity value. Okay, so if I'm at 3 millimeters for my notch and I'm looking at this line, I'll bring this over and this looks like a notch sensitivity value of something like, I don't know, 0.87. I write down in my notes here 0.86. So let's go with 0.86. All right. My fatigue concentration factor then is 1 plus 0.86 times my static value, 1.65 minus 1. Put this all together. My fatigue concentration factor in this problem, 1.56. Don't get dyslexic on me now. So finally, my fully reversed stress amplitude at B after all modifications. This is going to be my fatigue concentration factor, 1.56. This is amplifying the stress that I would have calculated if there were no shoulder at point B, which we calculated above using my over I is 216 MPa. Hopefully you're all starting to see how annoying these fatigue problems are. Put this all together, 337 MPa. That is the stress amplitude at point B under this particular situation. I want to quick bang out part C and then we'll do part D on Friday. All right, part C. Determine if the material will yield if the yield stress is 590 MPa. Okay. This one's pretty quick. We're told the yield stress here is 590 MPa. No yield. What does that mean? That means we're in high cycle fatigue. Because I have no plasticity. This is important because it means that we can apply that model that we previously talked about. A steel material, high cycle fatigue, we can apply. A prediction of number of cycles to failure, which remember, something like your stress amplitude over this variable A to the one on B. We're basically setting up that part D for this problem, which is estimating number of cycles to failure, that this is going to be a valid calculation. All right, so we hit 10:50. I was hoping to finish this problem today, but maybe we'll just take 5 or so minutes on Friday to do it. All right, that'll be it for today. Those of you with the exam tomorrow, I'll see you at 10 o'clock. Otherwise, see you guys on Friday.